Hey, welcome to the last presentation in the set of presentations on real numbers, and we've been looking at various types of numbers, and wow, what's this going on down here? What's going on in this diagram? And you can see it's what's called a set diagram or a Venn diagram, showing sets of different numbers. And what we're saying here is in the big box we've got the set of all real numbers, and within that group we started with what? Natural numbers, 1, 2, 3, etc. Went to whole numbers, which was negatives as well as positives, whole numbers. And hey, hang on, what's going on here? Integers, aren't they the same as whole numbers? Oh, what is in the set of integers that is not in the set of whole numbers? Integers are positive and negative, whole numbers are positive and negative. Hey, you might want to discuss that with your classmates and your teacher, okay? And it's saying the integer set is bigger than the whole number set, and the whole number set is bigger than natural numbers. And then we've got this bigger set outside called rational numbers, and that's what this is about. Rational numbers, what are they? You haven't seen them before, I don't think, not at this level. And then there are irrational numbers. I guess if it's not rational, it must be irrational. Okay, so I wonder what rational and irrational means in maths land. Rational and irrational people are people who can reason or not reason, but I don't think that means the same in numbers, does it? Let's go and see that, but I want you to just have a look at this introduction to how numbers are grouped together, and the biggest number set here that we're looking at in this course is the real number set. Later on there's something called the complex number set, or imaginary number set. Now that's something to look forward to as well. Let's come down and have a look at these rational and irrational numbers now, and a few screen clippings here from Hayes and Harris publications, so it's important to have that book there to refer to. So rational number, here it is, and I'm going to give you a hint. I'm going to call it a ratio now number, a ratio now number. Hey, what do we mean by ratio? Here it is. It's a number which can be written as a ratio of A over B, where A and B are whole numbers, and you can't have it over 0, because we haven't discussed that much yet, but you can't divide by 0, can you? B cannot be 0 there, not equal to 0, because that would be trying to divide a number into 0 parts. It really wouldn't make sense, would it? So you'll learn a bit more about that later on. So we've got really a different name for these. They are usually called fractions. So some of them are proper fractions, where the numerator is less than the denominator, and some of them are called improper or top-heavy fractions, where the number on top is bigger than the number underneath. And then mixed numbers, a whole with a fraction, can be changed to improper fractions, where you say in 1 there are 2 2's in 1, and 1 half there makes 3 halves. Okay, so the number of halves in 1 is 2, plus the extra half is 3. So you've got 3 halves. So they are all examples of ratio now numbers. And we don't call them ratio now, we call them rational. Okay, and whole numbers, of course, are also rational, because 5 can be thought of as 5 over 1, neg 3 as neg 3 over 1. So how about that? Okay, so we're going to start to put all these numbers into some order and some understanding, and look at them on the number line, because in maths, of course, numbers are our tools, and it's important to understand them. All right, well, let's have a look now at representing these with decimals, okay, and I think we referred to that a little bit in the last presentation. How do you convert ratio now numbers to decimals? Now, ratio now numbers or rational numbers can have a terminating decimal. That's one that stops. In other words, terminating decimal has a finite number of non-zero digits. Okay, so something like 3.45. We've just been doing some work in the last presentation on that. And so can this be converted to a rational number? Yeah, that's 345 hundredths, isn't it? Okay, 1 for the decimal, so it's 345 hundredths. So any decimal that stops and doesn't go on, and is exactly 3.45, can be changed to a ratio. And it's a rational number, therefore, a ratio of whole numbers, like we did with converting in the last presentation on decimals. So 4.256 is a terminating decimal. And is it rational? Yep, it's 4,256 thousandths. Remember, one for the decimal and one for each zero afterwards. Okay, so the 4 is 4,000 thousandths. Did you understand that? Let's just check that. 4 is 4,000 thousandths. Just checking they all cancel out, dividing top and bottom by 1,000. Okay, so there you have one type of decimal that will give a rational number. That's a terminating decimal. We can show it's rational like that. So here, when written in lowest terms, a rational number will convert to a terminating decimal. How do you know whether it stops? If the bottom line, the denominator, has no prime factors other than 2 or 5. Okay, so they are terminating decimals. So something like what? What can we have? 13, what would be a good one? 13 eighths. Okay, will convert to a terminating decimal because the only factors of 8 are 4 and 2. So, or 2 cubed actually, isn't it? Go 8 is 2 cubed, and there are no other prime factors, and so it should terminate. There's a little rule for you. When you're converting that to a decimal, it should be a terminating decimal. Okay, that should work. And we'll talk about conversion of those a bit later on. Let's go down and see if there's another way, or check the way of converting fractions by writing the fraction so it's denominator to the power of 10. And this is 1 for the decimal place and so on. So 3/5 here, we need to multiply top and bottom by 2, so you get the decimal system. Decimal, remember, base 10, dec. Okay, so 6/10, and then we can go to 0.6. 7/25. The 25's a problem. We want to make that into base 10. Multiply top and bottom by 4 is 28 hundredths. So it's 0.28. Same idea. Here's 5/8 as I promised you. With the 8s here, we've got to get to 10s. We looked at this in the last presentation. What do you multiply 8 by to get 10s or hundreds or thousands? You've got to go right out to thousands. So you multiply by 125, do the same top and bottom. So 5 out of 8 is the same as 625 out of 1,000. And so it's 0.625. So this decimal or base 10 system requires this changing to tens or powers of tens, isn't it? So there's our challenge. All right, get your head around that. That's important. It's pretty simple if you know what you're doing here. Okay, so come down. Let's look at another way of getting a rational number. So what's called a recurring decimal. Can you look at that word? And it recurs. A lot of people put reoccurring. It's occurring over and over again, so it's reoccurring. But we drop out the occurring in there. We just call it recurring. So occurring again and again is what recurring means in English as well. The same meaning in maths. So what's an example? A third has a decimal of 0.3 and it keeps going. So we sometimes write a 0.3 with a bar over it, or when it's only one number recurring, maybe just a dot. Means it keeps going and going. How would you like to see a little trick about how to show that 0.3 recurring is a third? You can go this way, but if I take it, let's have a look here. If I say, well, if I let x be 0.333 and it goes on forever, let's make it a whole number by multiplying by 10. So 10x is 3.3333, and they keep going an infinite number of times, never stops. In fact, I don't like putting 3 on there, and it just keeps going an infinite number of times. If I then say, well, let's from 10x take away x, so I'll put here take away 1x would be one lot of this, and it keeps going. If I take that away, 10x take 1x is 9x, and if I take all that away, I get 3. So x is 3 over 9, or 1/3. Okay, so that's a little way of taking a recurring decimal and trying to make it into a rational number, a ratio of integers, and then getting lowest terms by dividing top and bottom by 3, okay, or cancelling up here at this line. So, interesting. You never would have thought that would come out to be a ratio with so many decimal places not stopping, not terminating. Okay, but there's an example. So come down and let's have a look at the definition here. Recurring decimals repeat the same sequence of digits. It may not be just one digit. It might not just be a 3. It could be a pair, like 0.27 or something like that. And it never stops. It keeps going to an infinite number of places. So a rational number will convert to a recurring decimal if its denominator has at least one prime factor other than 2 or 5. So what can we say? Well, 1 over 3. 3 does not have a prime factor of 2 or 5. It's got a prime factor of 3. And here, what's another one? Well, let's take 4/15. It's got a prime factor of 5, but also 3. And if it's got another prime factor other than 2 or 5, it will give a recurring decimal. In other words, there'll be a set of digits that will keep repeating. Now, there's an interesting rule. Okay, you might look into why that's the case. Okay, I think it's got something to do powers of 10, mate. So if you've got 2 or 5, they are going to be more easily converted into a power of 10, aren't they? I wonder if you could use algebra to prove that. Could talk to your teacher or other students about that. Okay, let's go down and investigate some, get you to get involved yourself there. For example, 8 over 11, that's got a prime factor of 11. And here we are, it repeats itself. 7, 2, 7, 2, 7, 2. And we would write it like that. We use a bar over the 2 digits to indicate that pair recurs. And we could put a bar or a dot over the 3 to indicate that in a third. And here, sometimes some non-repeating digits take a while before the repeating digits occur. So, in other words, here you got 0.8 and then 3 and then it recurs. So you'd put it over there. And sometimes it's quite a few more non-repeating digits first before it starts repeating. So this is interesting. But where you have repeating digits, eventually you can convert this to a rational number. Okay, sometimes it's a little bit hard to do, and I showed you that trick with 10x and so on, but it would eventually give a ratio of integers. Interesting stuff, and this is new, I guess, at this level. So it's important to get your head around this because we're going to talk about some important irrational numbers later in your maths career. So come on down now and have a look at an example of this sort here. So write as decimals 7/9 and 5/11. So you can see here that 7/9 is 0.7 recurring. Now you could use technology here, or you could do the long division. I'm going to show you that in a minute over here. And it gives 0.7 recurring either with a bar or a dot over it. So we're going to try and divide 7 by 9. 9's into 7 doesn't go. Okay, so 9's into 7 don't go, and then 9's into 70. We'll go 7 9's are 63, and 7 over, and you keep putting the 7 over, and it keeps being 7 over. So that's why it's recurring. So you try to divide it out, and it gives that pattern. So it's 0.7 recurring. So it is a rational number, and because you've got here a prime factor of 3, is 3 as a factor there, then it will give you a recurring decimal. Only numbers which just have prime factors of 2 or 5 are easily converted to tens and will be an exact number of decimal places. Okay, what about 5/11ths here? Let's get rid of that. Sorry about that. What about 5/11ths? Let's try and divide 5 by 11. 11 into 5 doesn't go. 11 into 50 goes 4 11s are 45 and 6 over. Then 5 11s are 55 and 5 over. 4 11s are 44, 6. Oh, a pattern's starting to come out, isn't it? Every time you do a division after the first division, you start to repeat the same carryover number, the remainder that's left on division, and you get that pattern. So you would write it as 0.45 with a bar over the top. Okay, now here's an interesting one. 1 on 17 has a prime factor other than 2 or 5, hasn't it? 17 itself is a prime factor. So 17 is prime. So here, if you did that division, all of these digits repeat before they do it again. So it can be a whole range of digits there before they recur. All right, are you getting the hang of this? So out of it, we want to see that rational numbers are terminating decimals or recurring decimals. So here's some exercises for you. The idea is to write all of these numbers in a rational form, a ratio of 2 integers. A and B are integers, and where B is not nor. So I want you to pause the presentation and have a go, and I'll show you the rest of the set, and then down below there are the answers. So please don't do all the problems and get them all wrong. Don't perpetuate an error. As you do a couple, go and check your answers and then toggle back and have a look. Okay, let's look at the other ones here. 6 and 7 there. Okay, so have a go and try not to use your calculator for as many as possible until, some of them down here need a calculator, and you might need to use a bit of calculator help there if you've forgotten long division. All right, pause it and have a go. Let's go and have a look at the answers now. Okay, so there's 3E, the answers, and how did you go? I wonder if you're able to get this long one here by doing your own division by hand, or did you use a calculator? All right, how's it going? Let's go on and look at irrational numbers. Okay, so an irrational number, what is that? Well, I've got a couple here for you. They are ones that cannot be written as a ratio of 2 whole numbers. You can't write them as a simple ratio. Their decimals keep going. They're non-terminating and non-recurring. Because remember, a terminating decimal, one that stops, can be written as a ratio of integers by splitting it down into tenths, etc. And then a recurring one can be written as a ratio of integers. But the square root of 2 just keeps going, mate. That number which multiplied by itself gives 2, sorry, get rid of this now. That number that multiplied by itself gives 2 is a non-terminating, non-recurring decimal. It just keeps going. And pi, you've seen this before, hope you have. The circumference of a circle is pi times the diameter, or you could say pi is the ratio of any circle's circumference to its diameter. And that keeps going on and on. It doesn't stop, and it does not recur. It just generates more and more figures there. Okay, so they're examples of irrational numbers. Can't be written as ratios. This is important in your maths career later on to understand the difference between these two. Okay, obviously now, here's a little tidbit for later on. Obviously, if you use this, let's say to 3 decimal places, as root 2, and you try to multiply it together, it won't actually exactly give 2. Now, the calculator might round it off, but the square root of 2 is that number multiplied by itself gives 2. And it won't exactly give 2. Why? Because it needs all of these other digits forever to be exactly the number to as many places as you like which multiplied by itself gives 2. So there is only one exact answer. Only one exact answer to root 2. It is root 2. As soon as you start to play with decimals and you're going to round them off or not use an infinite number, you can't use an infinite number. An infinite number is never stopping. It just keeps going. Infinite number is the largest possible number. It is infinite, so you can't actually have it. So because you're not going to use all these digits forever, the only best way of representing an irrational number is like that. And the same with pi. If you start using some of these, but not an infinite number of them, which is impossible, then you're going to get an approximation. So this is the only exact representation of pi. Any decimal representation has some limitations because you haven't used an infinite number of decimal places. Quite a bit abstract there, isn't it? So come and look at that later on. If you're not sure of that now, don't worry about it. It's just a little tidbit to get you thinking. All right, let's go on and see what we can do. All right, so here on the number line, we're trying to show the difference between the rational numbers and the irrational numbers. Now, this is the real set here of real numbers on the number line, but we're not showing, well, we've got the wholes on there, the whole numbers, the integers, but we're not going to confuse the whole thing by trying to label all of them. What we're saying is rational numbers, there's one, a terminating decimal, there's a fraction, there's a recurring decimal, there's a whole number, there's a mixed number. So we're trying to show that on the number line, these come to precise points there, and you can make them a ratio of integers, rational numbers. And then there are some here, root 30. The negative is down there, so it's to the left of 0 on the number line. And root 30 is a non-terminating, non-recurring decimal. Neg pi. Pi is approximately, look at that sign. That means approximately down there somewhere, but you can't plot it exactly on the number line. Okay, you can't plot it exactly on the number line because you can't get an exact decimal for it. It's a non-terminating, non-recurring decimal, and that can't be represented easily as an exact position there. And root 2, approximately 1.414. Okay, and here's pi up here, approximately 3.14. So, do you get the idea? Irrational numbers have approximate positions there on the number line, but we can't actually land them precisely there because you cannot plot a number which has an infinite number of decimal places. Irrational. Fairly challenging stuff to think about. All right, well, let's keep going. And here we are, decimal representation of irrational numbers. So here, an irrational number neither terminates nor recurs. So there is an infinite number of decimal places, and it just keeps going. Okay, after the decimal, there's an infinite number of places. Okay, do you get it? Let's do something with it. Okay, so here we are, flash down to 3F. Okay, state whether the following numbers are rational or irrational. It may help to view the numbers in decimal form using your calculator. Just remember, rational are terminating or recurring decimals. Irrational cannot be written as terminating or recurring. Okay, I'll get rid of that. I don't know why that keeps coming up. So here, I want you to pause the presentation and have a go. And I'm going to show you the answers in a minute now. And just make sure as you do some stuff, check the answers, don't get them all wrong, and find out later. Don't perpetuate an error. All right, here we go. Here are the answers. All right, there's 3F. So I hope you're getting your head around this. You might have to get some help from your teacher and discuss it with your classmates. Always good to talk about maths and dialogue about it. Dialogue learning, talking about the stuff, really enhances your understanding. All right, that's the end of the presentations on real numbers. So there'll be more in the series for this Year 8 maths. So I'll catch you then. Cheers for now.